Okay, just moving on to the next exercise, and the reality is the teaching is the same, and I've done it including this what we call a horizontal shift, or they might call it a horizontal phase of -1, which simply means move the whole graph down 1. That's the only difference between the exercises. It does say to actually label this. It talks about using a calculator to work things out, and so the endpoints, we're told that to work out what the actual endpoints are. So at t equals -pi on 4, y will equal 2 cos 3 times -pi on 4 plus pi on 4. And so we end up with, and that's -1. We end up with cos of 3 times 0, which is 0, -1. And cos of 0, if you think of the cos graph, it actually starts at 1 at 0. So we get 2 minus 1, which gives me a value of 1. Now the next point to look at is, now I just realized I had made a bit of an error. I had written down 5 pi on 4 when it's actually at t equals 5 pi on 12. Now I've changed that. Now when we substitute, we get y equals 2 cos 3 outside of 5 pi on 12 plus pi on 4, or -1. So I get 2 cos of 3 times, now to work that out, that's 3 pi on 12 makes it 8 pi on 12, which becomes 2 pi on 3. -1 becomes 2 cos, 3 times that becomes cos of 2 pi -1. Now cos of 2 pi, if I think of my curve, it ends up at 1, so that's 2 times 1 minus 1. You can use your calculator, of course, and I get a value of 1. Now you were told to use your calculator, and this is something you've got to get used to. You don't need to do everything manually, and by using your calculator, you can get a fairly accurate sketch. We've worked out that at -pi on 4, and then the other side is at 5 pi on 12, which is just a little bit more than a quarter. So 5 pi on 12, we're at a value of 1. Typing that into your graphics calculator, you'll see that the curve is something a bit like that. And we're sketching. Sketching is a representation. It's not a Rembrandt. Okay, looking at question 2. The first thing I'm going to note is that I have an amplitude of 2. Now, because there's a 2 in front of the x, the period will equal 2 pi over 2, which gives a period of pi. So it's basically the period is halved. And this value at the end, minus √3, is the vertical translation or vertical shift. So that means that it is going to go down by a value of √3. Now I actually just watched the videos on the Cambridge online text, and I actually found that quite useful. So whereas I had shown you to do lots of things and to drew one and then to move it and then to move it, what they have looked at is to say, okay, well, let's take your basic, and we're told in this one to do from 0 to 2 pi. They said, okay, the amplitude is 2. That's fine. We have a period of pi. Don't need to worry about that quite yet. We'll put in our basic marking, which is pi on 2 and 3 pi on 2. But we have a phase shift of -√3. Now what you've got to do is to get an idea of what does that look like. Now √3 is of course smaller than 2, but bigger than 1. So it doesn't hurt to just type it into your calculator to get an idea, and it's approximately 1.7. So what we're actually doing is we're moving the middle line. Instead of being at 0, we're going down to root 3, which is approximately 1.7. So I'm going to put a dotted line to indicate this is our new midline, our new halfway point. Now, of course, it has an amplitude of 2. And so if we think of negative root 3 plus 2, that was negative 1.7, so it's just a little bit over there. So that's 2 minus root 3 is there. And now we have to go 2 further down, so I end up at negative 2 minus root 3. So our peak and our trough. So our amplitude goes up 2 from negative root 3 and down 2 from negative root 3. Now the other thing to remember is our period has been halved. So let's go back to that, and it's halved, so I'm going to put in pi on 4, 3 pi on 4. So we're halving all this so we can illustrate it all. 5 pi on 4 and 7 pi on 4. So instead of going up and down over 2 pi, it's going to go up and down over one set of pi. The other thing that they use, which I thought was good, they illustrated we're using sines. The sine starts at the middle, it goes up, back to the middle, down, up to the middle, up to the top, down to the middle, down to the bottom, up to the middle. And once I've put in those points, I'm then sketching a curve to show 2 sine 2x minus root 3. So there's an example you can follow. And the example, if you use the electronic textbook, is quite good as well. But there's one more part to it, and I think they're a little bit lax in their explanation there, but you may find that quite satisfactory yourself. But we have the next part says to state what the x-intercepts are. Well, the x-intercepts are when y equals 0. When y equals 0, okay, that's the x-intercept. So in this one, we're going to have lots of them. We're actually going to have 4. So 0 equals 2 sine 2x minus root 3. Take the minus root 3 over, and I get 2 sine 2x. Remember, you always move the minus before you remove the divide, and times. And so sine 2x equals root 3 over 2. Now, at this point, we've got to remember what sort of triangle does that work with? Well, 2, 1, root 3. There's your 60, which is pi on 3, and your 30, which is pi on 6. So I can see root 3 on 2, sine being opposite over hypotenuse. The opposite to be root 3, the hypotenuse to 2, tells me that 2x, or the angle 2x, is related to pi on 3. So there's a key to look. Now remember that because we're looking at 2x, we're told it's between 0 and 2 pi or 360. Then if we looked at x, that would actually have to be between 0 and 4 pi or 720. And that's one of the keys that we need to look at. And so when is it positive? Because that's a positive value. All stops to central. Sine is positive in A and in sine. So there's pi on 3 here, pi on 3 here, and so we have pi on. And so 2x will equal pi on 3. The next one is pi minus pi on 3, which is of course 2 pi on 3. Then we have to loop all the way around and up that little bit. So it's 2 pi plus pi on 3. And the last one is to go loop-diddy-loop, which is actually 3 pi minus pi on 3. So 2x will equal pi on 3, 2 pi on 3. This becomes 6 pi on 3, 7 pi on 3, and the last one is 9 pi on 3 minus pi on 3, which is 8 pi on 3. But that's 2x. So x will equal this divided by 2. Pi on 6, pi on 3. So 2 pi on 3 divided by 2 is pi on 3. 7 pi on 6. And the last one, if I divide that by 2, becomes 4 pi on 3. So we have multiple solutions. Now, a lot of this is going to be using some stuff in the past. I do believe some of you have struggled with this, so it is important that you do the practice, and that's why I've allocated a number for you to do. Okay, an example of 3B. So basically I'll be doing a few more practices of sketching because some of you might struggle with it, but the reality is it's not that bad. You just need to do a bit of practice and it comes fairly easily. So if you've got it, feel free to just start working on the questions, and if you need to refer back to more help, that's fine. First thing is 2 is the amplitude, 3 is the period change, and minus 4 means that it's moving 4 pi on 4 to the right. So if I do my little sketch, and I know that it has a period change, so the period equals 2 pi on 3. So it's reducing the period by 3. It's a third of your normal period, and it says to only do it for one full period. So 2 pi on 3 is the end of the period if we started at 0. Now if I want to divide that up into quarters, so in the middle is 2 pi on 3 times 4. The 2 into that once, 2 into that goes 2. And so in actual fact, if I now look at that, I have pi over 6 is my halfway point. So that's pi over 6. Here is a quarter of it, so 2 pi on 3, actually that's 1/4 of it, 2 pi on 3 is pi on 6. My mistake there. In the middle is actually 2 pi on 3 divided by 2, which is pi on 3. And of course this next one would be 3, dividing it by 4 and multiplying it by 3. In other words, it's 3 times pi on 6, which becomes pi on 2. So we've changed the period simply by dividing what we know the final period part, dividing it up into quarters. You can use calculators if you really struggle with that. So you might even translate it. Some of you will translate it and say, well, that's 180 is what pi is. 180 divided by 3 is 60 times 2 is 120. Okay, well 120 means halfway has to be 60, that's 30, and that's 90, and then put it back into radians. It's not too hard, and that's a good way to do things. We have a bit of a phase shift happening with the pi on 4. So we've already factored that in. We know that it goes up to 2 and down to -2 because it has an amplitude of 2. And so instead of starting, this is cos, instead of starting here, I'll just do a dotted line to show what the normal cos would look like. We're told that it has got to be moved along by pi on 4 to the right. Okay, so we've got to think, well, what's pi on 4? Well, that's 45 degrees. So pi on 4 is here. That's halfway between those two. That's 30, that's 60. Okay, that makes sense. So now this is my starting point. So I'll go halfway through there. That will be where it goes down to 0, starting point, down to 0. Halfway between there will be going down, and of course it's heading back up. Now the other one is, where do we go from there? There is another 0 point because we've moved along. So we end up with up, down, and going through like that. And so my sketch is the one that's in purple. So I still use it by doing part of it and then moving. I find moving the horizontal shift the last thing to do. Now if you change it into degrees, sometimes that's easier to think about. I know a lot of students do find that easier. Okay, you also have a graphics calculator that you can use to help you finding intercepts or roots using the functions of a graphics calculator can be useful. And 4 asks us to look for the period, amplitude, and range in each case. It's to sketch it. Remember, it's a sketch. It's not doesn't have to be brilliant. So we have the amplitude as √3. We have the period. So the period will be 2 pi on 3, which is just like that previous graph we looked at. And we have the horizontal shift being pi on 2, so it's moved pi on 2 to the right. So it says to show one complete circle. It doesn't say we can't start, that it has to start at 0. That's the other thing to remember when you see something like that. So let's have a look. We have no vertical shift, so I don't need to worry about moving the middle line. We have an amplitude of √3, so it goes up to √3, down to negative √3. The period is 2 pi on 3. Now I'm not saying it's cheating, I'm just going to use the values that I worked out in the previous one. Pi on 3, pi on 2, and pi on 6. Now I'm just going to sketch in what the sine graph would normally look at, going from 0 to the upper at pi on 6, 0 at pi on 3, lower, and back to middle. And so we draw in the sketch. However, we are told that it moves, it has a horizontal shift of pi on 6. So we have to move the entire graph along, of not pi on 6, pi on 2. So in other words, this value here is moved that far forward, which means this value here would have to be moved the same amount. And if we backtrack, and it's very easy to backtrack because this sort of fills in, we end up with the graph, and so the blue is the actual graph of y equals 3 √3 sine 3 side of theta minus pi on 2. Okay, young people, question 5 is that whole dilation, what does it look like, etc. So it's not a bad thing, it's fairly easy. Have a go at it. Enjoy.